Well, hello everyone. Welcome back to your favorite calculus class. Let me get my stuff here. We'll get started. We're going to talk about concavity and curve sketching in this section. So first of all, concavity means you've got your definition there. If a graph is concave up on an interval, then f prime is increasing on an interval. And we'll talk about concave down as well. Let me give you a picture here, for example. So to go back for a minute, you know how f prime, when we talked about f prime, it described the function f, f prime wherever we had our critical points, then if it was positive is increasing, negative decreasing, and so on, right? So the second derivative would actually describe the first derivative. So if the second derivative was positive, that means the first derivative's function is increasing. So for example, here's just an example of a function f that it shows, okay, on the picture. So you can see if I had, that tangent line, let's say that f prime, let's say it's f prime at 1, whatever it is, but the derivative here is like negative a third. And then for this tangent, maybe that derivative over here, maybe it's f prime at 3, but that derivative is 1, so it's increasing from negative 1/3 up to 1. And this derivative over here, let's say it's at 5, and let's say that derivative's like, I don't know, 2 over 1 or something, right? Slope of 2, that for that tangent. Anyways, the f prime is increasing, right? So if your f prime is increasing, right? So f double prime is describing f prime, meaning f prime is increasing. That's when you're going to get that shape of concave up. So that's describing the original function then. If f prime is increasing, then the original function is concave up. The original function must be concave up. It's got that little smiley to it. It's kind of parabolic, if you will. So all those tangents are on the bottom side of that thing, okay? Whereas if you're concave down, that means the second derivative is negative, meaning the original function is concave down because all these slopes of the tangents, if you were to name this slope like this f prime, maybe it's a third, and then this f prime is like -1, and this f prime is maybe -3. See how it's decreasing in value there, right? So the f prime is decreasing, so that means so that means all these tangents are going to be on the outside, if you will, and you're going to have this parabolic shape where you're concave down. Okay, so the second derivative is describing concavity. If it's positive, the original function is concave up. If it's negative, the original function is concave down. I think we'll solidify this with some examples here. So here's an example. I've got f of x equals a third x cubed minus x. So if you notice that we take the first derivative here, we've got x squared minus 1. Right? So we've got the derivative x squared minus 1. Let me factor x squared minus 1. So our first derivative, we've got on our first derivative test here, we got 1, we got -1. If we plug in -2, we got a negative times a negative, so we got positive. So the function's increasing, right? Plug in 0 and I got a negative, so then it decreases. Plug in 2 and then it into the f prime again, and we see that it increases, right? So there's what f prime tells us. Now let's take the second derivative. All right, so I'm taking this f prime, I'm taking the derivative of x squared minus 1. So I've got 2x. You can find the points of interest here, the critical points here. Let's say it equals 0. So x equals 0 for my second derivative. I'm gonna then say, okay, second derivative is 0. Let me test to the left of that, like f double prime of -1. I'm gonna throw it into the second derivative. So 2 times -1. So I got -2. So the second derivative is negative. That means the original function is concave down. Concave down because what that's saying is f prime is decreasing. Right? That's what it's saying. It's saying the f prime function is decreasing. Well, if the f prime function is decreasing, all those slopes of tangents are on the top side, meaning it has this shape to it, concave down. The original function must be concave down. Now let's plug in something to the right of 0, like 1. So we got 2 times 1, so 2. So the second derivative is positive. That means over here to the right of 0, it's concave up, right? So here's my original function, 1/3 x cubed minus x. We know it goes down to the right, down to the left, I'm sorry, up to the right, right? We can plot some points on there, you know, plug in -1, 1, you plot in these points, and you get your points here where you've got your relative max, got your relative min. We know it's increasing up to -1, it's increasing, and then we decrease in between, and then we increase again afterwards. And then in terms of the concavity, get a different color here. In terms of the concavity, we are concave down until 0, and then we switch to concave up. So we're concave down. Here's the concave down part, right? See how we're concave down there on that function? And then we switch to concave up. What color do I want here? Green. Kind of having too much fun with these colors. Then we switch to concave up after that x value is 0. Okay, and that x value is 0. See how we switch right here from concave down to concave up? That's called a point of inflection. So you have a point of inflection at the point 0, comma, and then plug the 0 into the original function, you get 0. You have a point of inflection at 0, 0. So a point of inflection means, in fact, let me jump to that definition for a minute, means your concavity switches. So for example, right here, you got a point of inflection because you're going from concave up, and it switches to concave down. This one's concave down, then it switches to concave up, right? This one's concave up, then it switches concave down, right? So if your concavity changes, again, it's got to change, right? You can't go concave up, concave up. That's not a point of inflection. All right, let's determine the open intervals on which the graph of 6 over x squared plus 3 is, I love my blue. I got to go back to my blue here. Is concave up or down. I'm going to think about this as 6x squared plus 3 to the -1. All right, so our first derivative, we got -6 x squared plus 3, now it's to the -2, chain rule 2x, so -12x over x squared plus 3, 20 squared. There's our first derivative. So I say, well, first of all, where's this thing? Where's my critical points? Well, from my numerator, where does -12x equals 0? Whenever x is 0, so there's 1 for our first derivative test. 0. Now, notice on the bottom, there's nowhere where f prime is undefined because x squared is always positive. Then I add 3, I'm always positive, and then I'm squaring it. So the bottom's always positive. There's no x value that can cause that denominator to be 0. We'll throw in something to the left like a -1. Then you got a -12 times a -1. So you got +12. Plug it, bottom's always positive. All right, so f prime -1, you got -12 times -1 over -1 squared. Again, the bottom is always positive. You got 12 over, this is always positive. So you got a positive over a positive, this is always positive. So the function's increasing. Plug in 1, you're going to get that thing to be decreasing. And then you're going to run through, now we're going to take the second derivative. Here's my first derivative, -12x divided by x squared plus 3 quantity squared. So I'm going to take the second derivative. So derivative of the top times the bottom minus the top. Derivative of the bottom, which is 2x squared plus 3, now it's to the first power, and then 2x. This is all over bottom squared. Okay. And then we're going to clean all this stuff up. So we got negative 12, x squared plus 320 squared. We got, what's that, plus 12. So we got positive 12x times the 2 times the 2x. So we got what, 48x squared. And then we got an x squared plus 3. X squared plus 3 to the 4. I'm going to take an x squared plus 3 out front. So I have, oh boy, take an x squared plus 3 out front. So I have negative 12 plus 48. Whoops, negative 12. And I have plus 48x squared over x squared plus 3 to the 4th. Again, this is our second derivative. And by the way, one of those cancels with one of those. I'm going to distribute that right there. So I got negative 12x squared minus 36 plus 48x squared all over x squared plus 3 to the 3rd. Then my second derivative, sorry about the mess, it's hard to write on this thing, is 36x squared minus 36. I'm going to take a 36 out. I got x squared minus 1. And that's 36. I got x minus 1, x plus 1. Okay, so my second derivative, I've got negative 1 and 1. I'm going to plug in, and I'm plugging it in right here. This is x minus 1, x plus 1. So I plug in like a negative 2. I've got a negative here. I got a negative here, negative here. So negative times negative. I got a positive on top. The bottom's always positive. So positive over positive, positive. The original function is concave up until negative 1. Plug in 0, you get negative. So you'd be concave down. Plug in like a 2. Again, I'm plugging it into f double prime. Plug in like 2. You'd be concave up. Again, I apologize for my limited window here. Okay, but let's show you a picture of this here. So we had f prime. Well, let's see, it was increasing and then it was decreasing, and then f double prime, we had a, let's see, we had a concave up, then we had a concave down, and then we had a concave up. All right, concave down, concave up, concave up right here. All right, and you can kind of see it over here. If you were to plot a bunch of points, right, plot a point, and you're like, hey, this thing's increasing, so I'm increasing until 0, but I'm concave up until right here at negative 1, and then I switch, right, and then I switch concave down, and then we go concave up again. But we're increasing this whole time clear until 0, and then we decrease afterwards. Okay. Talked about our point of inflection. You've got a point of inflection when the concavity changes. All right, so let's say we've got x to the 4th minus 4x cubed, and you're looking for points of inflection and the concavity again. So let's go straight to the first derivative, 4x cubed minus 12x squared. Let's take the second derivative, 12x squared minus 24x. Let's take a 12x out, and we've got x minus 2. So for our second derivative, we're going to have 0 and 2. And then we'll plug in like negative 1. Plug it in. I've got a negative from here. I got a negative from here. That's a positive. All right, so that's positive, so we're going to be concave up. And then I'm plugging in like 1, and I'm going to have a negative, so we're going to be concave down. Again, I'm plugging it right in here. Plug in like 3, and I'm going to have a positive, so we're going to be concave up. All right, so concave up, concave down, concave up. So we've got point of inflection at x equals 0 and x equals 2. So let's look at the graph here. We're concave up, then we switch. All right, we switch. I kind of like my blue. We switch concavity. We're concave down. Oops, I went too far. And then we switch again to concave up. All right. So that's the concavity discussion there, right? And our point of inflections again would be when we change concavity, we switch from concave up, concave down. So that's a point of inflection. Switch concave down, concave up, point of inflection again at x equals 2. So you got a couple points of inflection on that one. All right, so the converse of that theorem is not true. In other words, it's possible for the second derivative to be 0 at a point that it's not a point of inflection. So that's, for example, if you're concave up and then you stay concave up, right? That's not a point of inflection. If you're, you know, 0, if you're concave up and then you stay concave up, this is not a point of inflection. All right, again, you got to change concavity. You got to change concavity, and that's all that we're talking about on that. Okay. This is also talking about the second derivative test. You know, the second derivative will teach us about concavity, and depending on your textbook, they'll call the official second derivative test, meaning like they'll take um, they'll take a critical point off of the first derivative. So like let's say you have I don't know, here's your function. Critical points are -1 and 1. It increases, then it decreases, and then it increases. And the second derivative is concave down and then concave up. Okay. The second derivative test is saying officially, if I just, we already know that if I increase and then decrease, as long as I'm defined here, I have a relative max, right? And then if we decrease and increase, it's already apparent that we're going to have a relative or local min as well. Well, the second derivative test is just telling us, hey, if I know my critical points, I can just plug that in to the second derivative. So f double prime of -1. And I see that at -1, it's concave down. So if the function's concave down, I have to have a max up there on the actual function. And then if I plug in this other critical point into the second derivative, I know it's concave up. If f double prime of 1 is positive, well, that's got to be a minimum. Right? It's got to be a minimum. So I just like to run both the first and second derivative and just do it all at one time. Okay, but that's what that's talking about. If you get a critical point, it's concave up right there. You're gonna have a local min. You're gonna have a local max. If you have another critical point, it's concave down. Okay. All right, let's go ahead and find some extrema for this one here. So f prime, we've got -15 x to the 4th plus 15x squared. Let's take a -15x squared out. So we have x squared minus 1. Set that equal to 0. Factors, so we got 0, we got 1, we got -1. And then we just plug in, -2. Let's plug it in. That's an x minus 1 right there. Let's plug it in. -2. If I plug in -2, I get -15. I get -2 squared, -2 minus 1, -2 plus 1. So I got negative here, I got negative here. This is a -15 times a positive number, so negative there. So this is negative, so the function decreases. Plug in like -0.5, and I've got a negative, yeah, negative, and then negative a half minus 1, I get another negative. Negative a half plus 1, I get a positive, so this will end up being positive, so then we increase, right? So we decrease, then we increase. Well, if I decrease and then increase, by the way, if I do my f double prime at negative 1, I know, hey, I got to have a relative or local min right there, right? Plug in like a half, so you have a negative from the negative 15 times a half squared, right? Negative 15 times a half squared would be negative. Negative a half minus 1, I get a negative. Negative a half plus 1, I get a positive. So this thing is positive on that. So then well, I'm sorry, what did I plug in? I plug in a half. Half minus 1, half plus 1. Yeah, negative, positive. So then we increase. And then after 2, or plug in 2, and we got negative times a positive, negative times a positive times a positive, so this is negative there. Okay. So it looks like we got increasing, we got decreasing. Right? So this function then, in this case, is telling us, well, we're going to have a relative min, decrease and increase. We're going to have a relative max at 1 as we increase and then decrease relative max there, right? Again, you can go on to the second prime if you would like to, okay? And this is just showing the relative max, relative min. Notice it increased and then it continued to increase, right? It was concave up. If you did the second derivative, then it was concave. All right, what if you were to sketch a graph here, this x squared plus 4 all over 2x? What I'm going to do here also, I'm going to continue to use the calculus, of course, but I'm also going to incorporate my understanding of pre-calc of my rational function. So like, what's my vertical asymptote? Take my denominator 2x, make sure it's factored, it equals 0. So I know this function has a vertical asymptote x equals 0. Think about your horizontal asymptotes for a minute, or the limit as x goes to infinity here. The degree of the top is 2. The degree of the bottom, x to the 1 power, is 1. If n is greater than m, right, the degree of the top is greater than the bottom, there's no horizontal asymptote, but there's actually a slant or oblique asymptote. And if you remember from your pre-calc, what we did was we would divide this x squared plus 4 and we divide it by 2x. And we'd rewrite that, right? So we would rewrite this function, which would end up being 1/2 x plus 4 all over that 2x. 4 is our remainder, so you get this 1/2 x. You do all this junk, you get 4 is your remainder, right? So 1/2 x plus remainder over that divisor. So 1/2 x plus 2 over x. All right, 2 over x. That right there was our slant asymptote. Okay, so y equals 1/2 x, because as x goes to infinity, this is going to 0. Okay, so the y value is approaching that line, up 1, right 2, up 1, right 2. So here's the slant asymptote. Okay, so it's going to kind of be following that. Now let's actually do the derivative on this thing. So we take the first derivative, derivative at the top times the bottom, minus top, derivative at the bottom, all over bottom squared. So we got 4x squared minus 2x squared minus 8 all over 4x squared. So that's 2x squared minus 8 over 4x squared. So that's x squared minus 4 over 2x squared, or x minus 2x plus 2 over 2x squared. All right, so in terms of the f prime, you've got 2 and negative 2. So 2, negative 2. Where's the derivative undefined? 0. Okay, so we're going to be examining all around that. We're going to throw in negative 3. And we got a positive on the top, positive on the bottom. So we know the function increases. We throw in negative 1. We got negative on the top, positive on the bottom, so negative. So then the function decreases. Throw in 1. Again, I'm throwing it back in here. Right, throw in 1. And we got negative on the top. We got a positive on the bottom. So we got negative. So it decreases again on this thing. And then on 3, plug 3 in. We got a positive on the top, positive on the bottom. So then it increases. Okay. Now we take the second derivative. Sorry, I'm doing my best here with my little laptop. Derivative of the top times the bottom minus the top. Derivative of the bottom squared. So I've got 4x to the third minus 4x to the third plus 16x all over 4x to the fourth. So I got 4 over x to the third. That's my second derivative. So my second derivative, I'm just looking, where's this thing? 0 under undefined to 0. So I'm gonna look around 0. I'm gonna plug in f prime and -1. I got a negative, so this thing is concave down. Plug in f double prime of 1 again into the second derivative here. F double prime of 1 will be positive, so concave up. Okay, and then you could just plot some other points in here to kind of get a feel for this thing. You know, throw in -2, 0, 2, well, 0 is undefined, so you can throw that in. You've got your vertical asymptote there, but you could throw in, let's throw 2 in, and you've got into the original function, right? So you got 8 on the top over 4 on the bottom, so 2, 2, and then 2, 2. Anyways, you graph a few points here. We know it's concave up. It decreases from 0 to 2, but we're concave up, and then it's going to increase after, and it's going to approach that. A plot like -2, it spits out -2. We know this thing's concave down, but we're increasing until this -2, and then we decrease, but we do stay concave down on that, right? It's kind of approaching that. Anyways, I've got a better little graph right here. You can see it. We're increasing, but we're concave down till 0. Concave up, but we're decreasing here, and then we increase after. Right? We've got that vertical asymptote right down the middle. This is that slant asymptote, y equals 1/2 x, x over 2, and so on. All right, let's talk about some more conceptual stuff here. And these are the procedures that we kind of just went through on that last one here. Let's say we got a first derivative given to us. So here's our first derivative. They're already given it to us. And you know what? I'm going to write that. I'm going to take a negative out so that is -2 plus x minus 2. That just kind of puts it. So we got 0 and 2 on our derivative test, right? Because we're going to use this information to kind of analyze the function. We plug in -1. Well, this will be positive, but then we got to apply the negative. So that's a negative times a negative, so we got positive. So function increases, plug in a 1. We got a negative times a negative is a positive, so then it increases again on this thing. And then after if I plug 3 in, I got a negative 3 squared, so -9 times positive is a negative times a positive, so then it decreases. Now let's take the second derivative, and let me rewrite this here. I've got this is 2x squared minus x to the third, in other words, -x cubed plus 2x squared. Now let me take that derivative. So the second derivative of -x cubed plus 2x squared. So -3x squared plus 4x. And then, sorry, I didn't do this very well. Take an x out. Set equals 0. So we got x equals 0, and then -3x plus 4 equals 0. So x equals 4/3. Okay. So on our double prime, we were at 0 and 4/3 are those critical points for that second test. And I'm going to plug it in right here. So plug in like -1. I got a negative times a positive is a negative. So we're concave down. And then plug in like 1. So 1 times -3 plus 4, positive times positive, positive. So then we're concave up. Plug in like 2. 2 times positive times a negative, negative. Then it goes concave down. And again, it says use the graphing procedure to sketch the general shape of the graph of the original function. We don't know exactly what it looks like, but we do know it increases and then to 0, and then it increases again. So it increases, and we're concave down until 0. So we're concave down, but we're increasing. Concave down, but we're increasing. Okay, so we got some concave down, but increasing going on there. We increase again, but we got to switch it. We got to switch to concave up until 4/3. So 1/3. So till about right here, concave up. And then we'll go concave down, but just know that after 2, we got to decrease. So after 2, we got to decrease. So like at 2, since we increase and decrease, this is a relative max, right? So we got the max right here. Notice it's concave down right there. And this right here is about 4/3. Well, that's not very good. But anyways, 1/3 more. So anyways, you kind of get a feel for it. This is a little bit better. We increase, but we're concave down. Then we switch to concave up in between here, but we're still increasing. We're increasing. And then we finally switch here to concave down, but we're not decreasing until after 2. What if we're giving it to us in this form, right? So they're giving you the graph f prime. What I would do is I would say, okay, f prime. What are my critical points? Where's f prime equals 0? Right here. They're giving you the critical points. Even though we don't even know what the original function is, we just have the graphs here. Looks like -2 and 2 are our critical points. That's where it hits f prime. And then anything to the left, if I was to plug in like f prime and -3, I know it's positive up here. So the original function must be increasing. Then it's all negative down here. All these y values are negative. So the original function must be decreasing, since this is a picture of f prime, right? It's a picture of f prime. And then all the y values are f prime are positive after that. So f prime would be positive. So the original function is then increasing. Now let's look at the red one. So f double prime. Where's f double prime equals 0? Well, right there, hits 0. There's our critical point. There's where f double prime equals 0. And if I plug in f double prime of like -1, it's right here. It's a negative y value, right? It's negative. So anything over here is negative. That means the original function must be concave down. If f double prime is positive over here, that means the original function must be concave up. Let's see if we can get a picture of that. From f prime, we had -2, increasing, then we decreased, and then we increased. F double prime, 0, we were concave down, then we're concave up. All right, so the function's got to increase, decrease, increase. Well, that's out. We don't increase, then decrease, then increase. We got to increase until -2. This is out. Again, we got to increase to -2. Then we got to decrease, and then we got to increase. That's out, right? So we're between A and B here. Now we got to be concave down until 0, and then concave up after 0. This is not concave up. Okay, let's check this one. Do we increase and concave down? We're concave down to 0. We increase until -2. Sure enough, we increase. And then we decrease in between here, and then we increase after. And we're concave up after 0. Sure enough, that's the one right there. All right, last example here, and we'll get you on your way. This is giving us a graph below to fill in the information, whether it's positive, negative, or 0. So when it's asking about f of a, the point at a, this is functional value, right? So this is y value. What's the y value at a? Well, the y value at a is positive. Y value at b, that's 0. Y value at c is negative, right? F prime. Well, what's F prime talking about on the graph? Well, you got to think about your tangent lines, the slope of the tangents, right? F prime is the slope of the tangent line. So A, if I was to draw the slope of the tangent A, I know that's a negative slope. If I'm going to draw the slope of the tangent at B, I know that's a negative slope. If I was to draw the slope of the tangent at C, that slope is 0. Now, F double prime is your concavity. So let's look at A. At A, can you tell that you are concave down at A? You're concave down. You're part of that interval that's concave down. So F double prime would be negative. At B, it switches. So it switches from concave down, and then it switches. See how it switches to concave up right at B? So that's a point of inflection. So F double prime would be 0, or F double prime is undefined, but the only option on this one is 0. So we've put 0 in. And then F double prime at C down here, right? C is right there, is concave on that. So that's what you're kind of thinking as you're going through that. All right, that's it. Thanks for watching. See you next time.